Who do you want to receive routing information from? Well, you only want to receive routing information from authentic routing devices, meaning those routing devices that you've deemed as an administrator to be part of your routing domain, part of your routing infrastructure, and that the information they contain is valid, accurate information that can be shared with other routers. So through the process of authentication, we ensure our routers authenticate every single routing packet that they receive from their neighboring routers. And as a result, when they authenticate those packets, they are ensuring that, with EIGRP and OSPF as an example, they only form neighbor adjacencies with routers that they can successfully authenticate with. They only exchange routing information with routers that they can successfully authenticate with. So this is going to make sure that we avoid false routing information being injected into our routing table. It might be from a malicious rogue device that's been set up by a malicious user to send or inject false routing information in our environment, or it might be by accident. A user plugs in a router while they're studying for the certification exam, and they set up a routing protocol, and it happens to start injecting false routing information in the routing domain. Well, through the process of authentication, we ensure that our routers do not accept or utilize that false routing information because the packets aren't authentic. They're not coming from a router that we have been able to successfully authenticate those packets with. When it comes to routing protocol authentication, you have two different options: simple password authentication and hashing authentication. Now, it's important to realize that not every routing protocol supports both of these. For example, OSPF, RIP, and ISIS support simple password authentication, whereas every routing protocol supports hashing authentication. So if you're implementing EIGRP, hashing authentication is your only option. So let's look at the simple password authentication process. This is also known as plain text authentication. And what we have here is the message, for example, the OSPF hello packet or the OSPF link state advertisement that's being sent from one router to another router in the environment. This key is being attached. And what is that key? It's the password in this case. So if the password is Cisco, which is not recommended, but let's say it was, it's appended to the message. So that way there, when the receiving router receives it, it checks this key against the key it has configured locally on the router. And if they match, then that means it's authentic, meaning it came from an authentic router that we are able to authenticate with, and as a result, it is a legitimate routing update packet, and we will use it. However, this key is in plain text. It's plain text. It's not a simple password authentication, but it's plain text, meaning it's in the clear. If this is captured at all, this packet, the malicious user will be able to read the password that's being utilized. So simple password authentication is an option, but it is recommended that you avoid it if you want to provide the highest level of security for your router. Avoid it. Now, let's clarify something here. It's better than not having authentication. So if for some reason you can't use hashing authentication, then this is better than having no authentication, because at least you're making sure that the routers are only accepting legitimate information from authentic devices. The next option is hashing authentication. This is much more secure than simple password authentication because the router doesn't send the key itself, meaning it's not sending the password across the network. It's sending a message digest instead across the network. And we want you to make sure you understand that this is not encryption at all. The packet itself is not encrypted. The hash itself is not encrypted. So if it's captured, you can see the hash and you can see the original packet. What we're doing here is we are protecting our routers and the routing information that they receive. So that way they don't take in inappropriate routing information and use it. So this is not encrypted. We can still see the contents of the packet. However, now, instead of sending the password in the clear, that key, we are creating a hash based on the routing update and the algorithm that's being utilized and the key that's being utilized as part of the overall hashing process. And this hash is generated, and it's the hash that's sent across with the packet. So let's say we were using EIGRP in this example, and this was a hello packet or an EIGRP update. This packet would be sent in the clear. The hash would be sent in the clear, but it's this hash that's going to be utilized to make sure that the packet is authentic. So over on this side, the router receives it, and it has to calculate on its own a hash based on its local keying information that it has. So we just received this particular routing update from this router. Okay, based on the keying information we have locally, what hash should they have sent? And then we generate that, and we compare the two hashes. If they match, it's authentic. We accept it. We utilize that information. But if the hash doesn't match, then that was not from an authentic device. So, although it says here nobody can eavesdrop, read the whole statement. Nobody can eavesdrop on the line and learn the keys. They can see the information in the packet. They can see the hash itself, but they can't learn the keys that were being utilized in order to generate the hash. That's why you have a higher level of security when using hashing authentication instead of simple password authentication.